Okay, so this is the circling ball problem on Mastering Physics, and the question asks, if you have a ball that's moving in a circle, a vertical circle, on a string, the ball has a mass of m and a radius, or the string length is L, then the question is asking about the difference in the tension at the bottom of the string compared to the tension when the ball's at the top of the circle. So just to get started in this question, the first thing that I did was I thought, since it's asking about something about tension, it's certainly asking me something about forces. And so given that, I went ahead and decided to do the natural thing, which is to draw free body diagrams. And specifically to draw free body diagrams at the very top point, and then draw a free body diagram at the very bottom point. So here are my diagrams. I kept them pretty simple. I just said that there was a gravitational force downward at the top, and that has the size of mg. And then there's also going to be a tension force, which would have to be directed downward at the top. And I didn't know whether one of these was bigger than the other, but so I just drew them the same size. Then I went to the bottom, and I had a really similar diagram, except for at the bottom, the gravitational force is now the same size as this one and still pointing downward, but the tension force is now upward. And I would expect that the tension force would be much larger at the bottom. And so I drew it that way. And then I noticed that, that if, in order to move in a circle like this, I know that the ball has to have acceleration that's always pointed towards the center of the circle, unless it's speeding up or slowing down. And so at those 2 points, at the top and at the bottom, there would be no need for acceleration parallel to the motion, because presumably this is when it reaches its minimum speed, and this is when it reaches its maximum speed. So right at the very top, it wouldn't be slowing down or speeding up, and therefore the entire acceleration would just be the radial or centripetal acceleration towards the center of the circle. And similarly at the bottom it's at its maximum speed, no longer speeding up or slowing down, so that acceleration is going to be entirely towards the center of the circle. And I expect that the acceleration would be bigger here than it is here, because it's moving faster at this point. And I remember that centripetal acceleration is related to the speed of the object squared. So given all that, I know these are my directions for acceleration, and so then I also know that the acceleration will be the amount of acceleration needed to keep it on a circle, and the net force will provide the centripetal force towards the center of that circle, which is equal to the mass of the object times its speed squared divided by the radius, and in this case the radius is L, the length of the string. So all that tells me that at the top, the net force at the top is going to be downward, and it's going to be equal to the mass of the ball times the speed of the ball at the top squared, divided by the length of the string. And then similarly, at the bottom, the net force will be upward. It will be equal to the mass of the ball times the speed squared, divided by the length of the string. And notice one thing I'm trying to do here is I'm trying to keep my subscripts to make it really obvious to me whether I'm talking about the quantity when it's at the top or the quantity at the bottom, because those are the two instants in time that I'm trying to differentiate in this problem. So once I have this, I've got my free body diagrams, I know something about my net force based on the motion, then I can put those pieces together and I can say that the net force, in this case, is the sum, by magnitude, it's the sum of the gravitational force and the tension force. And so I just say that the tension force at the top plus the gravitational force is equal to that required net force to move it on the circular path. And I solve for the tension at the top, and I get this. Next step is I do the same thing at the bottom. So tension at the bottom, but notice the net force is going to be the magnitude of the tension minus the minus mg, or minus gravitational force. And so there I would say the tension force at the bottom minus mg equals the magnitude of the centripetal force, or the net force here. So I write that out and I solve for the tension, okay? And I noticed that, some things are not surprising, that at the bottom, the tension has to be big enough to provide the centripetal force plus some extra to balance out the gravitational force. Whereas at the top, the tension force is less than the net force, because the gravitational force also provides some of that downward force when it's at the top of the motion. So then this finally gets me to the point where I can start to move towards the thing that the question is actually asking me about, which is the difference between the two tension forces. And I find that the difference between the two tension, this should be T bottom minus T top. The difference, because the bottom is going to have more tension than the top, the difference between those two tensions, just by subtracting these two equations, is equal to the mass over the length times the difference in the squares of the speed plus 2 mgh. Okay. So in some sense it looks like I'm almost there, but I noticed that the problem told me that it wanted a solution not in terms of these speeds at the bottom and the top, but in terms of just the mass and gravity, okay, and possibly the length of the string. And so, given that, I need to figure out some way to find out something about these speeds at the bottom and the top. And right away, I noticed that it doesn't really give me any information about those speeds, so that seems a little bit strange. So I'm just going to sort of assume that I'm going to be able to figure that out somehow. And but I do notice that as the ball moves around the circle here, I would expect that the energy, total energy of the ball would stay constant. Or in other words, the kinetic energy of the ball plus the gravitational energy of the ball Earth system at any point would be a constant. And there, I'm assuming that there's not a significant amount of air resistance, but given what is available to me in this problem, it seems like those are reasonable assumptions to make. Okay, so in that case, I would expect that the ball would have more speed and therefore more kinetic energy at the bottom because it loses gravitational energy as it goes from the top down to the bottom. Okay, or it's going to transform that gravitational energy into motion energy. Okay, so energy-wise, if I assume that the energy stays constant as the ball moves around the circle, then I can say that the kinetic energy at the bottom is equal to the kinetic energy at the top plus the gravitational energy at the top. Okay. There I'm making a little bit of a decision to say that I'm going to call this, I get to choose wherever I want the 0 point of gravitational energy to be, so I'm going to particularly choose the 0 point of gravitational energy to be at the bottom, and then the top point will have more gravitational energy, and the amount more will be based on how much higher it is, which I also notice to be twice the length of the string. Okay. So then substituting in the equation, the kinetic energy at the bottom is 1/2 mv bottom squared. The kinetic energy at the top is 1/2 mv top squared. And then the difference in kinetic energy is just going to be equal to the mass times gravity times twice the length of the string, which is how much higher it is at the top than it is at the bottom. And notice I've done one extra step in going to the second line. I've also gone ahead and subtracted this kinetic energy from both sides to bring it over onto the left side of the equation, because I know, looking ahead, that I'm looking for a difference between the speed at the bottom and the top. Right? So already this is starting to look a whole lot like what I need to find for my equation here, and the only thing that I have to do is I have to get rid of the factor of 1/2 and the factor of mass. And so I notice mass shows up in all three, so I can cancel the mass out from all three terms. And then if I just multiply all three terms by 2, this one just becomes v bottom squared, this one becomes just v top squared, and then I multiply this term by 2 and I get a 4. Right? So it would be 4 times g times L, where I've now canceled out the mass. And now I'm almost there, so I just take this expression for the difference in the speed at the bottom and the speed at the top squared, and I plug it in over here in my expression for the difference in the tensions, and sure enough, everything, you can check this yourself, but everything simplifies dramatically, and I end up with the difference in tension, again, bottom minus top, difference in the tension at the 2 points in the circle is equal to 6 times the mass times gravity. And there are, in some ways, this is a kind of a surprising result, because it tells me that in this kind of a situation where an object is moving in a vertical circle on a string, there are a couple of things that don't influence the difference in tension. Right? One of them is that the speed of the ball at the top or at the bottom doesn't matter. Right? It's actually only the difference in speeds that matter, and that is only related, or the difference in the speed squareds, and that's only related to towards gravity. Okay. And another thing is that the length of the string doesn't actually matter. So that tells me that if I do the same experiment with a small string and a big string, I end up getting the exact same effect. So what I find is that if the string were longer, the difference in the speed squares would be bigger, but it would be bigger in just the right amount to cancel the length of the difference in the length of the string in the denominator. So that all factors out, and you just get that the difference in the two tensions is equal to 6 times m times g. And I can also make sure that in fact these units are correct, and sure enough, tension is in newtons, and m and g combined to give newtons. So that all looks really promising. So that's it.